At this very moment, the cosmos is expanding, not through violent blasts or impacts, but because space itself is stretching uniformly in all directions. The separation between galaxies and stars is accelerating over time. Scientists refer to this driving force as dark energy, which largely governs our reality. Comprising almost 70% of all existence, we inhabit a cosmic ocean where small islands of matter perpetually drift farther apart, never to rejoin. On this journey, you will traverse immense voids that, by all accounts, should not be there. You will uncover the reasons for the universe's apparent silence regarding other civilizations and witness what awaits when ultimate emptiness finally prevails. If you are prepared to confront the profound disquiet of true nothingness, hit the like button and let's commence. Observe your surroundings, all that you perceive, all that you feel. Every individual you know owes its existence to matter. Your physical form, this world, our star, and every luminous point in the nocturnal heavens are composed of atoms drawn together by gravitational force. However, decades of scientific scrutiny have verified this. The sum of all that constitutes almost nothing. When scientists quantify the universe's total constituents, they discover that conventional matter, the type-forming stars, planets, and living beings, comprises under 5% of all existing things. The other 95% remains unseen, and the majority of it is not simply a vacuum. Picture gathering every observable galaxy, every star contained within them, every planet circling those stars, and every nebula of gas and dust floating in between. Now, if you were to compress all that matter, its presence would be negligible relative to the universe's vastness. The cosmos's average density is approximately 6 hydrogen atoms per cubic meter. The vacant room you currently occupy contains trillions of times more particles than an equivalent volume of outer space. The universe is not primarily composed of objects. Rather, it is largely defined by absence. However, this void is far from straightforward. When astrophysicists commenced their research into galactic rotation, they stumbled upon an anomaly that, by all scientific understanding, ought not to be present. Stars situated at the periphery of galaxies revolve much more rapidly than the gravitational pull from observable matter permits. Based on all current physical understanding, those stars should break free. The galaxy itself should disintegrate. This identical paradox manifests on even grander scales. Clusters of galaxies comprising hundreds or thousands of individual galaxies exhibit velocities that ought to lead to their dispersal. Considering only visible matter, these formations should have disintegrated billions of years prior, yet they persist. Scientists refer to this unaccounted-for mass as dark matter. Dark matter neither emits nor absorbs light, nor does it reflect any form of radiation. Observatories are unable to detect it because light travels directly through its substance. Its existence is solely inferred through its gravitational influence. Dark matter's mass exceeds that of all visible matter by a ratio greater than 5:1. For each atom comprising stars, planets, and living beings, at least 5 times that amount of dark matter silently sculpts the cosmos. It creates immense, diffuse halos surrounding galaxies. These halos, stretching well beyond their observable boundaries, dictate galactic rotation, gas accumulation, and stellar birth locations. Were it not for dark matter, galaxies such as the Milky Way would be unable to form. The cosmos would persist as a diffuse haze of particles, incapable of coalescing into organized structures. This is not merely a hypothesis. It is substantiated by numerous independent observations. Gravitational lensing demonstrates that light from remote galaxies deflects significantly more than observable matter alone can account for. Measurements of cosmic background radiation indicate density variations that necessitate the presence of dark matter to align with present-day observations. Simulations of cosmic development only yield plausible galaxies when dark matter is incorporated. Dark matter is an undeniable reality, and it exerts a dominant influence over the universe. At this very moment, dark matter traverses your body. Trillions of particles stream through you each second. Unseen and unhindered, they penetrate Earth, the Sun, and even whole galaxies without interacting. You can't sense them, You can't impede them, yet your galaxy's formation depended on their presence. Here lies the initial unsettling reality concerning emptiness. The majority of existence remains unseen. Much of what molds reality is imperceptible, and this unseen matter itself isn't uniformly distributed. Upon charting the universe's vast structure, astronomers made a surprising finding. Space is not uniformly filled with matter. Rather, it constitutes an immense cosmic web. Slender strands of dark matter extend for billions of light years, directing the development of galaxies along their expanse. At the points where filaments cross, galaxy clusters emerge as concentrated clumps of matter. Immense areas are situated between these filaments. Containing virtually nothing, these are termed cosmic voids by astronomers. These voids are far from minor spaces. Certain ones extend for hundreds of millions of light years. Within them, galaxies are exceptionally uncommon. Even dark matter grows scarce, gravitational pull diminishes, and organization dissipates. Traversing a vast void at light speed would require more time than Earth's entire existence. Light that commenced its voyage prior to the evolution of complex life on this world would continue its passage through the void even now. The universe is largely governed by these voids. The majority of cosmic space is devoid of galaxies, stars, or even dark matter. Instead, it's occupied by expanding void. The luminous formations we observe are slender barriers and strands encircling immense pockets of near vacuum. It is at this point that emptiness turns dynamic. Gravity stands as the sole force capable of opposing cosmic expansion. In areas of dense matter, gravity maintains structural cohesion, but in regions where matter disperses, particularly within voids, gravity's influence wanes. The force that then predominates is termed dark energy by astronomers. Dark energy exhibits behavior unlike matter. It neither aggregates nor condenses. It does not diminish in strength as space expands. Rather, it seems to be an inherent characteristic of space itself. Each cubic meter of space holds dark energy, and as space expands, additional dark energy emerges. The more vacant a region grows, the greater dark energy's supremacy. This results in a perilous disequilibrium. Matter exerts an inward pull, while dark energy exerts an outward push. Within dense areas, gravity continues to prevail, galaxies stay whole, stars remain gravitationally linked, and planetary systems endure. However, in the immense vacant expanses between structures, dark energy holds absolute sway. Data indicates that voids enlarge more rapidly than the universe overall. Matter flows away towards more concentrated areas as the empty zones expand. They grow increasingly vacant and potent with the passage of time. This isn't an arbitrary movement, it's an irreversible progression. The cosmos inherently progresses towards a state of emptiness. This is because emptiness amplifies the force propelling expansion with each passing billion years. A greater portion of the universe shifts from being gravity-controlled to dark energy-controlled. More formations become detached, and more linkages are severed. When viewed from within a galaxy, this phenomenon seems imperceptible. It appears as though nothing in your vicinity is separating. Stars appear stationary, and the heavens seem unchanging. However, if you sufficiently widen your perspective, the underlying arrangement becomes undeniable. Material is withdrawing into distinct, separate areas. The cosmos isn't gradually becoming empty, rather it's being excavated. While dark matter constructed the framework enabling galaxy formation, it's powerless to halt expansion. Dark energy capitalizes on these spaces, elongating them further, and guarantees their permanent openness. The significance of void lies in the universe's inherent imbalance. It possesses a predisposition towards fragmentation. Material coalesces temporarily, drawn together by gravity into stellar bodies and galactic systems. Yet, dark energy functions ubiquitously, steadily intensifying as cosmic space dilates over time. It overcomes gravitational forces across increasingly vast dimensions. The cosmos resembles a landscape undergoing erosion in its structure. Temporary peaks of substance emerge, yet the vast sea of void continues to enlarge. This process, which erodes everything, isn't something for the future. It's occurring continuously, moment by moment. Cosmic space broadens annually. Empty regions increase in size over billions of years. Additional formations become detached. Furthermore, this represents merely the initial stage. For when the void reaches a sufficient magnitude, it accomplishes more than just dividing galaxies. It starts to obliterate them entirely from existence. It is at this point that the cosmos turns genuinely frightening. The most immense formations within the universe are not galactic systems. They are not groupings of galaxies. Instead, they are the expanses situated among them. As astronomers commenced charting the cosmos across genuinely vast dimensions, they anticipated discovering matter distributed uniformly, gradually diminishing in density with increasing separation. However, they uncovered something considerably more peculiar. Material was organized into slender partitions and threads, creating an immense universal network. Within this network existed colossal areas that held virtually nothing whatsoever. These particular zones are termed cosmic voids. Empty regions are not minor intervals separating galaxies. They constitute vast spatial expanses. In these areas, galaxies are exceedingly uncommon or completely non-existent. Certain ones extend for hundreds of millions of light-years in width. Others attain dimensions so immense they defy the predictions of our current theoretical frameworks. To grasp the extremity of this situation, envision compressing the entirety of the observable cosmos to the dimensions of Earth. The Milky Way galaxy would be finer than a strand of human hair, and the empty spaces between galactic filaments would represent land masses of nearly absolute vacuum. The greater part of the universe resides within these empty regions. Upon conducting extensive surveys to enumerate galaxies, astronomers discovered that most of the cosmic volume contains virtually no galaxies. Instead, galaxies inhabit slender envelopes encircling immense pockets of near-vacuum material. Material accumulates along the edges, leaving the interiors empty. Consider soap suds as an example. These bubbles are devoid of internal substance. The material forms slender barriers enclosing vacant areas. The cosmos appears similarly at larger scales, except these bubbles span hundreds of millions of light-years. Within a typical void, you might encounter a single galaxy where millions should be present. The density of matter plummets to a minuscule fraction of the cosmic average. Even dark matter becomes scarce. Gravitational pull diminishes, structure dissipates. Nevertheless, these voids ought not to be so empty. According to conventional cosmological models, gravity should have had ample time to draw matter back into even the most desolate regions. The universe is ancient, yet not infinitely old. Formations this hollow should be exceptionally rare. However, they are not. One of the most extreme instances ever discovered is an immense cosmic expanse, hundreds of millions of light-years across, containing virtually nothing at all. In a volume where thousands of galaxies should exist, merely a few dozen are detectable. This degree of emptiness is so profound, it defies statistical expectations. Traversing such a void at the speed of light would require more time than complex life has existed on Earth. Light that began its journey when the earliest animals emerged would still be moving through the darkness today. These are not mere gaps, rather, they are immense cosmic abysses. When astronomers simulate the universe on supercomputers, starting from the initial moments after the Big Bang, voids emerge organically. Matter flows along gravitational gradients, draining out of low-density regions. As it accumulates into dense filaments over billions of years, the most vacant regions grow even more desolate. Yet a challenge arises. Actual voids are expanding at a quicker pace than predicted by simulations. Observations indicate that cosmic voids enlarge more swiftly than areas containing matter. Their perimeters extend outwards, driving galaxies further apart. As a region grows more vacant, its expansion rate accelerates. This force is termed dark energy by astronomers. Dark energy neither coalesces into clusters nor diminishes in strength over distance. It functions as an inherent characteristic of space itself. As space undergoes expansion, dark energy accompanies it. Generating additional space results in the creation of more of the force that drives space apart. This provides an advantage to voids. Within areas of high density, gravity continues to oppose expansion. Galaxies stay gravitationally linked and clusters maintain their cohesion. However, inside voids, gravity is feeble. There is scant matter to offer resistance. Dark energy exerts absolute control. This leads to an accelerating phenomenon. Material streams from voids towards more concentrated filaments. When matter departs, gravitational force diminishes further. With gravity's weakening, dark energy intensifies the acceleration of expansion. Over time, the void expands, becoming increasingly vast and vacant. This state is not one of balance, but rather one of disequilibrium. The cosmos is configured to prioritize void over eons. While voids expand, matter recedes into progressively finer filaments. The universe's large-scale structure extends, its threads lengthen. Within a galaxy, linkages become less robust. This phenomenon is imperceptible. No alterations seem to be occurring in your immediate surroundings. Celestial bodies revolve, planetary systems maintain their steadiness. However, if one observes from a sufficient distance, then the arrangement becomes clear. The cosmos isn't becoming denser with galaxies. Instead, the space between them is becoming vacant. Furthermore, these empty regions are not merely devoid of space. They possess distinct thermodynamic properties. Electromagnetic radiation traversing extensive voids experiences an energy reduction. Light particles ascending from the weak gravitational field around voids exit marginally colder than when they entered. This impact is delicate yet quantifiable. It leaves subtle traces within the cosmic background radiation permeating the universe. These traces reveal a significant fact. Empty regions are growing more rapidly than anticipated. The decrease in energy surpasses what gravitational forces alone can account for. An unknown force is elongating the spatial fabric that photons traverse within the void. Dark energy causes these areas to expand, thereby extracting energy from radiation as it moves through them. The most vacant areas of the cosmos are growing colder than anticipated. This indicates that voids are not merely inert spaces abandoned by matter. Rather, they are dynamic contributors to the universe's development. They become frigid and detach themselves from the broader cosmos. Eventually, this leads to a universe fragmented into isolated pockets. Galaxies situated at the boundaries of empty regions encounter opposing forces. Gravitational attraction draws them towards proximate matter, while dark energy propels them outwards via the expanding spatial fabric. Currently, gravity prevails in concentrated areas, but along the peripheries, the equilibrium is changing. Ultimately, these empty spaces will transform into perpetual obstacles as cosmic expansion intensifies. The vastness of distances becomes such that no transmission can traverse them. Photons originating from one boundary of a void will never arrive at the opposite side. Interaction becomes unfeasible. Interplay ceases. This separation is permanent. The empty spaces guarantee that the cosmos will break apart into unlinked territories. These will never engage with each other anew. Every galaxy group transforms into an isolated entity encircled by ever-growing vacancy. This emptiness expands at a rate exceeding any possible traversal. This phenomenon is not merely a prospect for a far-off epoch. It has already commenced. Observations indicate that galactic clusters, positioned on opposing sides of extensive voids, are accelerating apart. The rate of expansion exceeds gravity's compensatory power. With the passage of time, additional galaxies drift out of range, propelled by the enlarging universe. Instead of being objects, the universe's grandest formations are expanding voids. This redefines our understanding of the cosmos's vastness. Your mental image of the universe might be a huge space packed with galaxies. Yet in actuality, galaxies serve as mere embellishments on the exterior of a far vaster phenomenon. Emptiness stands out as the defining characteristic. The universe isn't a location populated by objects. Rather, it's a dynamic process that continuously generates distance. While dark matter constructed the framework and gravity brought structures together, dark energy capitalizes on the voids, expanding them until these structures grow isolated and delicate. the cosmic network is progressively attenuating. The threads that formerly linked galaxy clusters are now being drawn tight. The barriers that once defined cosmic voids are retreating. Ultimately, the entire cosmic network disintegrates into isolated threads. The voids neither contract nor refill. Instead, they perpetually enlarge. This underscores the importance of emptiness, for when a void reaches a sufficient size, it doesn't merely distance galaxies, it severs them from each other's observable existence. Such expansion generates spatial zones that are causally isolated. These are locales where occurrences can no longer exert mutual influence. Beyond mere expansion, the cosmos is fracturing into distinct segments. Furthermore, these segments are not uniform. While certain areas retain their density and luminosity for an extended period, others transform into frigid, desolate expanses much more rapidly. The universe undergoes an uneven aging process, emptying itself from within. The present-day sight of abundant galactic filaments enveloped by darkness represents a transient configuration. As time progresses, the darkness proliferates and the filaments attenuate. The most immense entity within the cosmos isn't a discernible structure, rather it is the expanding void separating all other elements. Upon grasping this, emptiness ceases to be a mere backdrop and assumes the role of the primary subject. Throughout the majority of human civilization, the cosmos was perceived as perpetual and immutable. Stars were considered stationary and galaxies were believed to be permanent fixtures. It was once presumed that space itself served as a static backdrop for unfolding events. This premise proved erroneous. During the 20th century, astronomers ascertained that the cosmos is undergoing expansion. Galaxies are observed to recede from each other, not due to their propulsion through space, but rather because space itself is undergoing expansion. Continuously, fresh distance is generated between entities that were formerly in closer proximity. Initially, this cosmic expansion appeared uncomplicated. Had gravity been the prevailing force across cosmic distances, the expansion ought to have gradually decelerated. The expectation was that matter would progressively draw the cosmos back into cohesion, or at a minimum, impede its enlargement. However, empirical data presented an alternative narrative. Upon examining remote stellar explosions, astronomers determined that galaxies in earlier epochs were expanding at a slower rate than they are presently. The cosmos was not experiencing deceleration, rather, it was accelerating. The spatial expansion was gaining momentum. That particular force is termed dark energy by astronomers. Unlike conventional matter, dark energy does not exhibit similar behavior. Its concentration does not diminish with the universe's expansion. Instead, it seems to maintain a consistent energy density for each unit of spatial volume. With the expansion of space, an increasing amount of dark energy emerges, accelerating the separation of space. This phenomenon carries significant implications. The universe we can observe isn't expanding straightforwardly. Instead, it's becoming restricted. Light's velocity is constant. While no object can exceed that speed, space itself isn't bound by this constraint. Across sufficiently vast distances, cosmic expansion can propel entities away more swiftly than light can traverse the intervening space. A demarcation, known as the cosmic event horizon, exists. Past this point, galaxies are retreating at such a rapid pace that their emissions will never arrive here, regardless of how long they radiate. Expanding space will cause their light particles to be elongated and retarded, perpetually lagging. The moment a galaxy passes this threshold, it ceases to be part of our observable reality. It continues to exist and develop, yet it can no longer influence us, nor can we perceive it presently. This boundary is located approximately 16 billion light-years distant. Galactic systems close to this limit are nearing the point of vanishing. Their illumination reaches us currently solely because its voyage commenced a considerable time ago. Prior to expansion moving them excessively far, the disquieting reality is as follows. The universe we can observe is diminishing, not in physical dimensions but in accessibility, not in spatial extent but in available data. Annually, countless galaxies traverse the event horizon. Their subsequent light is irrevocably blocked. As time progresses, an increasing portion of the cosmos becomes inaccessible. This phenomenon is imperceptible to you. You won't witness galaxies suddenly ceasing to exist. Upon viewing a far-off galaxy, you are perceiving it in its state from billions of years past. By the moment its emissions reach us, that particular galaxy might already be too distant to observe. Certain galaxies captured in deep field photographs are no longer present within the cosmos we can perceive. Their current existence is eternally gone. This alters our understanding of remoteness. Within a universe not undergoing acceleration, every galaxy would eventually become discernible, provided sufficient time. Light would gradually traverse the widening void, but accelerated expansion nullifies that expectation. The rate of expansion increases more rapidly than light can counteract. The greater an object's remoteness, the quicker it withdraws at immense separations. The fabric of space extends with such velocity that light particles are unable to ever bridge the gap. They journey perpetually without advancing. The cosmos separates into areas that are perpetually cut off from each other, and this segregation intensifies. Far into the future, the dividing line will shift closer. Galactic systems currently discernible will pass beyond the horizon and disappear. The total amount of matter we can observe diminishes over time. Ultimately, merely systems held together by gravitational forces will remain perceptible. Our immediate galactic cluster, comprising the Milky Way, Andromeda, and several dozen lesser accompanying galaxies, is gravitationally cohesive. These particular galaxies will not separate. As a matter of fact, Andromeda is approaching the Milky Way. Over the course of several billion years, they are destined to coalesce into one enormous galaxy. All entities situated beyond that particular cluster are departing. More distant galactic clusters are presently accelerating out of our grasp. The void separating us and them is expanding at a rate that outpaces gravity's ability to keep them cohesive. Within tens of billions of years, all galaxies beyond our local group will have traversed the event horizon. The nocturnal heavens will then feature merely a single vast galaxy alongside a few dim accompanying bodies. Any indication of the broader cosmos will have vanished. Astronomers of the future will gaze outward to perceive a tiny, solitary system enveloped by profound darkness. They will possess no empirical evidence that countless other galaxies ever came into being. The universe's background radiation will have diminished to an undetectable level. The expansion will become imperceptible. Through their viewpoint, the cosmos will seem unmoving, diminutive, and devoid of content. Their perception will be incorrect. The cosmos will remain immense, continue its expansion, and still encompass areas forever hidden from their sight. However, the data necessary to uncover that reality will have been obliterated. This is not mere conjecture. It stems directly from observed expansion velocities and thoroughly validated physical principles. The cosmos is not solely expanding, it is concealing itself with each passing moment. Data becomes irretrievably lost. Transmissions sent out today will never arrive at the majority of the universe. Communications dispatched into the vastness of space are fated to dissipate completely. Interstellar communication over immense distances grows unfeasible. Such isolation additionally imposes a strict boundary on exploration. Not even theoretical advancements can surmount this challenge. Journeying at the velocity of light would offer no advantage. Space itself is expanding more rapidly than any vessel could traverse. The cosmos establishes an impediment not composed of substance, but of spatial configuration. Galaxies are not merely distant in the conventional understanding, they are withdrawing into insignificance. The diminishing observable cosmos brings about an additional outcome. It fundamentally alters the narrative of cosmic history. We presume the universe we perceive accurately reflects the entirety of reality. Yet, if expansion progressively deletes information, then prior epochs might have revealed more than we will ever witness. Proof of previous cosmic formations might have already vanished. It is possible we are currently inhabiting a universe that has lost memory of some of its own constituents. The universe we can observe is not an exhaustive chronicle. It represents what persists following eons of obliteration. This understanding redefines the concept of the void. The emptiness signifies more than mere spatial distance. It denotes the annihilation of information. The cosmos systematically denies entry to its own elements, not through force, but through an unyielding process. It neither detonates nor implodes. Instead, it extends until any link becomes unachievable. Furthermore, this process is accelerating. Here lies the dreadful result of dark energy. It doesn't directly obliterate matter, rather, it eradicates proximity. Ultimately, it guarantees that all things will be isolated. Each galaxy transforms into an island. Each island then floats towards its own boundary. The cosmos will not meet its end in flames or shadow. Rather, it will first conclude in quiet. And a section of space, once hushed, will remain that way eternally. The cosmos, by this time, should be vibrant. It's approaching 14 billion years of age. Stars have been developing for more than 13 billion years, with many of them having originated long before our sun, each orbited by planets. These planets, predating Earth by billions of years, some of them circle in areas conducive to liquid water, where chemical reactions might grow intricate and where life could potentially emerge. Even if intelligent life arises only seldom, the statistics become staggering. Within the Milky Way galaxy alone, there are hundreds of billions of stars. Modest projections propose that billions of planets could be found in life-sustaining areas. Projecting this across trillions of galaxies, the cosmos should be densely populated with intelligent societies. Some would be nascent, others venerable, and many would be millions or billions of years more developed than humanity. Despite this, when we gaze into the cosmos, we discover emptiness. No fabricated transmissions, no modified stars, no immense energy-gathering edifices, no undeniable evidence of intellect. This inconsistency is termed the Fermi paradox. Enrico Fermi first expressed this in 1950, presenting a straightforward question with profound ramifications. Where are all the others? The paradox is not philosophical in nature. It is mathematical. For a civilization to expand throughout a galaxy, faster than light travel isn't necessary. Even by progressing at a mere fraction of light speed, whether through self-copying probes or unhurried interstellar relocation, a species could fully investigate a galaxy. On the grand scale of cosmic time, a mere few million years is negligible. The Milky Way stretches beyond 100,000 light-years and has existed for over 13 billion years. If just one civilization had developed millions of years before us and decided to spread, its traces should be universally present. Yet it's not. For many decades, researchers have sought radio transmissions that could only be of technological origin. The premise was clear. Natural cosmic emitters create interference, which consists of random wideband signals. In contrast, technology creates distinct patterns, specific frequencies, recurring impulses, and an underlying mathematical framework. We constructed radio telescopes designed to survey millions of channels concurrently. We monitored stars in our vicinity, then those further away, and eventually vast regions of the galaxy. We detected no sound. Occasionally, an odd signal would manifest, a sudden surge, a sharp peak, always something unanticipated. More detailed examination uncovered natural causes, pulsars, magnetars, interstellar interference, and even household microwave ovens. The quiet continued on Earth, leading researchers to widen their scope. Sophisticated civilizations would necessitate enormous energy reserves. A rational strategy would be to gather a considerable portion of a star's energy output. This would modify the star's emitted light in discernible ways, generating unique markers that no natural occurrence could imitate. Investigations covered hundreds of thousands of stars, yet no verified proof of star-scale engineering was uncovered. In more recent times, astronomers started seeking atmospheric indicators on far-off planets, chemical disparities that could only be generated by industrial processes. Human-made contaminants, dissipated heat, and unusual gas compositions would be expected. Up to now, every planetary atmosphere investigated is in line with natural chemical processes. The cosmos stays silent. A comforting theory suggests that perhaps intelligent existence is remarkably scarce. It could be that the progression from chemistry to biology rarely takes place. Perhaps our planet Earth is a singular cosmic occurrence. Should that be the case, we are solitary yet secure. The alternative theories are considerably more ominous. The Great Filter theory posits that a virtually impassable obstacle lies between a planet's genesis and the emergence of a galaxy-wide civilization. This barrier annihilates most societies before they can expand. This filter might be in our past. Perhaps intricate life forms rarely, if ever, develop. Perhaps intelligence itself is a mere chance occurrence. In that event, we are fortunate to have endured. Alternatively, the filter could be in our future. Each civilization ultimately creates technologies it cannot manage. Atomic armaments, designed epidemics, synthetic intelligence, and ecological breakdown. Conceivably, the period separating technological prowess and self-annihilation is brief, lasting merely a few hundred years. If such is the situation, the quiet serves as an admonition. However, a different scenario exists, directly linked to the cosmos's inherent void. Civilizations might not be uncommon, rather they may simply be unable to encounter one another. Universal expansion places a harsh restriction on interaction. Societies need to be sufficiently proximate in both space and time for communications to bridge the divide before expansion separates them. This period of convergence could be much narrower than we instinctively anticipate. A radio transmission originating from the galaxy's opposite edge requires 100 millennia to reach its destination. Should a civilization endure for a shorter duration, the message would arrive subsequent to its demise. Over distances between galaxies, this issue turns insurmountable. Transmissions require eons to traverse. When a communication finally reaches its target, the originating galaxy might already be inaccessible. Expansion elongates signals, diminishing their strength and redshifting them beyond detection. Even if societies project their presence into the emptiness, the void consumes their utterances. Two distinct cultures might inhabit adjacent galaxies and remain perpetually unaware of each other's existence. The cosmos could teem with intelligent life, yet remain practically mute. This quietude intensifies with time, as dark energy hastens universal expansion. The count of galaxies able to transmit messages diminishes, spatial zones grow causally separate, intercommunication becomes perpetually unfeasible. We might have joined the cosmic dialogue either belatedly or prematurely. Should sentient existence be just now appearing throughout the universe, the epoch of interaction could still await us. Nevertheless, expansion guarantees that this opportunity will be fleeting. Galaxies separate more rapidly than societies can develop and establish connections. This perspective redefines the Fermi paradox. The cosmos might not lack life. Instead, it could lack convergence. Societies emerge, gaze into the universe, perceive stillness, and then vanish. They remain forever unaware that others underwent identical fates elsewhere, kept apart by ever-expanding spatial and temporal dimensions. We are attuned to a cosmos replete with unmade contacts. This potentiality is profoundly disquieting, for it implies that the quietude is not transient but inherent. It is intrinsically woven into the very fabric of space-time's geometry. The cosmos fosters solitude, not togetherness. Civilizations, even if they overcome their own internal threats, confront an insurmountable external peril. Due to cosmic expansion, regardless of their technological progress, the majority of the cosmos will forever be beyond reach. No vast interstellar civilization exists for us to find. No help from other stars is on its way. Each civilization emerges in solitude, exists in isolation, and perishes by itself. They are kept apart not by animosity, but by distances expanding more rapidly than light can traverse. The genuine terror of the void is not the universe's hostility, but its utter apathy. The cosmos permits intelligence to emerge fleetingly in dispersed regions, then guarantees these regions can never connect. Stars are not communicating, they are moving away from one another. As the universe ages, it grows increasingly silent. Its demise is not abrupt, it won't conclude in a fiery collapse or chaotic fragmentation. Its dimming is already underway. Throughout space, stars are consuming their fuel. Through nuclear fusion, hydrogen transforms into helium, emitting light and warmth that permeates the void. This mechanism has energized the universe for eons, seeming everlasting. Celestial bodies are engines with a limited energy supply. With each moment they shine, they deplete irreplaceable hydrogen. Across vast cosmic timescales, this reserve eventually depletes. Researchers observing galactic development found that the birth of stars reached its maximum billions of years prior. In the past, the cosmos shone much more brilliantly than it does now. During that era, galaxies often collided, compacting gas and triggering bursts of nascent stars. Currently, cosmic expansion has dispersed galaxies, making encounters less common and gas clouds sparser. The universe has already moved beyond its most prolific period. Approximately 1 trillion years from now, the creation of stars will essentially cease. The fundamental hydrogen required to fuel new stellar bodies will either be trapped in inert remains or too widely dispersed to coalesce. No fresh suns will emerge anywhere, yet the encroaching darkness won't descend instantaneously. Lesser stars persist. Dwarf red stars consume their fuel at a leisurely pace, considerably more efficiently than solar-type stars. A few will radiate for tens of trillions of years, serving as the final consistent light emitters in the cosmos. Nevertheless, even these are transient. Gradually, these ultimate stars deplete their energy, nuclear fusion ceases, and each transforms into a dim, defunct stellar body. Ultimately, they become a white dwarf, a neutron star, or a black hole. Eventually, no stars will remain throughout space. The cosmos transitions into what scientists term the epoch of stellar remnants. Galaxies cease to emit light. They evolve into aggregations of inert bodies floating through the gloom. White dwarfs gradually lose heat, emitting their residual warmth into the void. Neutron stars decelerate their rotation. Brown dwarfs, which are failed stars, drift through space, frozen and inactive. The cosmic temperature steadily declines. As space expands, radiation attenuates. Energy becomes progressively more diffuse. While not truly empty, this state signifies utter depletion. Across periods beyond comprehension, even the last traces vanish. White dwarf stars gradually chill to absolute zero, transforming into black dwarfs. These celestial bodies are so frigid and dim that they are virtually undetectable. Neutron stars meet an identical end. Their movement decelerates and encounters grow infrequent. Subsequently, only black holes persist as substantial formations. Black holes appear to last forever. For many years, scientists thought nothing could annihilate them, yet quantum mechanics unveiled an unsettling reality. Black holes emit energy via a phenomenon called Hawking radiation. Black holes gradually shed mass. They dissipate particle by particle. Minor black holes disappear rapidly, whereas supermassive ones require considerably more time. This can extend for up to 10, 100 years, yet even these are not everlasting. Once the final black hole dissipates, the cosmos reaches a critical point. No substantial, ordered formations continue to exist. All that's left is an almost homogeneous expanse of low-energy particles floating through an ever-accelerating, expanding cosmos. This condition is known as heat death. According to the second law of thermodynamics, entropy invariably rises. Energy disperses, disparities equalize, and systems progress towards a state of balance. Heat death isn't a sudden dramatic occurrence. Rather, it represents the ultimate equilibrium at this juncture. The cosmos has attained its peak entropy. No thermal variations remain to be utilized. There are no energy differentials, nothing to fuel movement, chemical reactions, or cognition. Time continues its flow, yet stasis prevails. Particles separate further from one another as cosmic expansion persists. Separations become so vast that interactions are rendered virtually unfeasible. Every particle finds itself isolated within its own expanding cosmic domain. The cosmos doesn't empty due to the destruction of matter. Instead, it empties because matter becomes dispersed. Even data starts to lose its significance. Information necessitates structural variations that are capable of being measured, contrasted, and analyzed. With the universe's expansion and cooling, data disseminates into scattered pieces. Ultimately, no observer would ever be able to reassemble it. The cosmos loses its self-awareness. This isn't a lapse in recollection, it's a breakdown in connectivity. Even though data might technically endure within particle states, it is dispersed so thoroughly that its reconstruction becomes impossible. The energy needed to retrieve it surpasses the total energy present in the universe. From a pragmatic standpoint, it ceases to exist following heat death. The cosmos embarks upon an epoch extending beyond human understanding. Innumerable trillions of years elapse without alteration. Cosmic space keeps on expanding and particles persist in their separation. However, quantum mechanics does not permit the existence of absolute nothingness. Energy constantly fluctuates even within the most desolate vacuum. Subatomic particles emerge and vanish momentarily. These variations are minute, transient, and typically hold no significance. Yet with an infinite duration, improbable events become certain. Far into the future, quantum fluctuations might occasionally coalesce into small, organized arrangements. The majority would disappear instantly, yet a few might endure for brief periods. This gives rise to one of the most peculiar predictions in contemporary cosmology. Within an eternal, vacant universe, random fluctuations are more apt to generate isolated instances of consciousness than to reconstruct a fully structured cosmos. These hypothetical intellects, known as Boltzmann brains, would materialize fully formed, complete with memories, thoughts, and sentience. Subsequently, they would dissipate back into chaos mere moments later. From their own vantage point, they would undergo the experience of existence. This notion is profoundly disturbing. It posits that in a universe enduring eternally, simulated observers could vastly outnumber authentic ones. The majority of physicists contend this implies our comprehension of probability, cosmology, or awareness is insufficient. Nevertheless, the underlying mathematics persists. The more vacant and enduring the universe grows, the more peculiar its ultimate states become. And this entire phenomenon originates from a single cause: cosmic expansion. Dark energy guarantees the continuous expansion of space. Matter never coalesces again, structures never reform. There will be no reversion to density, no subsequent opportunity for complexity. The universe does not undergo cycles. Instead, it disperses. Each instance of order is transient. Every structure exists on borrowed time. What renders this terrifying is not the universe's eventual demise. All things conclude, what makes it truly frightening is that the universe's end eradicates the very conditions enabling anything to hold significance. No observers, no documentation, no remembrance that anything ever was. Furthermore, this is not mere speculation founded on tenuous theory. It stems directly from thoroughly validated physics. Thermodynamics, quantum mechanics, and general relativity operating in concert. The universe remains indifferent. It is unconcerned that it once harbored galaxies. It is equally unconcerned that it once generated life. It continues to expand regardless, and the more it expands, the nearer it approaches a state where nothing of significance can ever transpire again. This represents the protracted triumph of emptiness, not abrupt, not aggressive, but utterly complete. The universe's emptiness is not coincidental. Rather, it directly results from its fundamental laws. The universe's age is approximately 13.8 billion years. While that may seem ancient, it is merely a brief span compared to what lies ahead. Stars are destined to continue radiating light for trillions of years. Black holes will endure for durations so immense they surpass nearly any conceivable numerical value. The universe's ultimate cold, diffuse state will persist longer than all preceding eras combined, yet intricate structures only emerge during a confined period near its inception, early in cosmic history. The early universe was excessively hot and uniform for atoms to persist. Matter and radiation were inextricably linked. Chemical reactions were impossible. With ongoing expansion, temperatures fell, atoms materialized, and gravity started drawing material into celestial bodies like stars and galaxies. Significantly later, a contrasting issue arises. The universe's expansion disperses matter excessively, leading to energy becoming overly diffused. The creation of novel structures ceases. Existence relies on an equilibrium point between these divergent conditions. This equilibrium state is transient. The genesis of stars commenced several hundred million years following the Big Bang, reaching its zenith approximately 10 billion years in the past. From that point onward, the pace has significantly decreased. Currently, the cosmos generates fresh stars at a mere fraction of its historical production speed. The majority of the stellar-forming gas has either been utilized or incorporated into enduring celestial remnants. The universe's expansion hastens this reduction as galaxies increasingly separate from one another. Encounters grow infrequent. Without such impacts, gaseous nebulae remain uncompressed. Lacking compression, stars fail to ignite. The universe's expansion subtly halts the mechanisms enabling intricacy. This transformation is attributable to dark energy. Initially, its impact was minimal. Gravitational forces prevailed, and structures developed. Gradually, as cosmic space enlarged, dark energy's power intensified compared to that of matter. Presently, it dictates the universe's macroscopic dynamics. This explains the cosmos's seemingly organized yet vast emptiness. Concurrently, concentrated areas persist on a local scale, whereas voidness predominates universally. Galaxies stay whole, yet the expanse separating them expands more rapidly than gravitational forces can counteract. This positions the cosmos in an intermediate phase. Our existence occurs subsequent to the formation of structures, yet prior to the expansion obliterating their effects. This constitutes an unstable situation. It represents a fleeting period nestled between two extensive epochs, during which intricacy cannot exist. There is no assurance that any aspect of this stage will endure. At this very moment, galaxies are traversing the universe's event horizon. Photons originating today from numerous cosmic locales will never arrive at our position. Over time, the quantity of causally linked areas within the cosmos diminishes. Data vanishes, not through violent means, but irrevocably. This outcome does not necessitate cataclysmic occurrences. It merely demands ongoing expansion. Across sufficiently vast timescales, even systems held together by gravity grow detached from each other. They are not annihilated, but rather merely distanced beyond the possibility of interaction. The cosmos does not eliminate structure outright. Instead, it severs connectivity. This bears immediate implications for anything reliant on energy transfer, interplay, and reciprocal influence, encompassing existence, cognition, and recollection. With ongoing expansion, available energy grows more limited, disorder rises, and energy differences diminish. Operations decelerate, subsequently ceasing. This is not a philosophical concept, it represents the application of thermodynamics across universal dimensions. The second law of thermodynamics assures us that organization is transient. Dark energy makes certain that no force can reassemble this order. After its dispersion, the cosmos is not cyclic. It does not revert to an earlier state. When matter becomes excessively diffuse, no process exists to undo this condition. As distances increase, gravity's pull diminishes, yet cosmic expansion persists. This clarifies why intricate structures emerge early and for a short duration. It's not that the cosmos prefers life, but rather that life can only come into being before the vast emptiness prevails. The very principles that facilitated the creation of galaxies also guarantee their inability to endure perpetually as interconnected entities. The identical expansion process that sufficiently cooled the nascent universe for atoms to materialize will ultimately render it too cold for any events to transpire whatsoever. Viewed this way, our presence isn't a marvel, instead it's contingent. Our being stems from the universe having traversed a transient arrangement where its density, both temperature and temporal conditions, were in harmony. That particular arrangement is, even now, in the process of dissipating. With each passing second, space undergoes expansion. For every billion years that elapse, the number of interconnected regions steadily decreases. Any process dependent on interaction grows increasingly difficult to maintain. This particular trajectory shows no signs of reversal. The cosmos is not progressing towards a spectacular finale. Rather, its trajectory points towards a state of inconsequence. This is a condition where occurrences still transpire within localized areas, yet nothing exerts a significant influence upon anything else. Once this state is attained, the initiation of anything novel becomes impossible. The cosmos transitions into an empty expanse. This isn't due to the disappearance of matter, but rather because immense distances render everything insignificant. This is precisely why the void evokes terror. It's not because it's characterized by violence, nor because it arrives abruptly, but rather because its advent is utterly inescapable. The very architecture of the universe guarantees that anything existing within it for a short period will ultimately become isolated, dispersed, and consigned to oblivion. The void does not represent a foundational layer within the cosmos. Instead, it signifies the ultimate terminal condition. At this very moment, your existence unfolds within the sole epoch where that ultimate condition remains sufficiently remote for the universe to convey a sense of vitality. This particular period is receding gradually and without cessation. Should you find this video enjoyable, kindly remember to give it a thumbs up and subscribe. Your support makes a substantial impact and contributes to the channel's expansion.